Today I want to talk about some simplified version of graphene. There are different versions of this. This is like a polymer with different versions, but I'm going to focus on the most interesting one from our point of view, which is called polyacetylene. And we are going to describe this with so-called Su-Schrieffer-Heeger model. And we'll see that it actually also gives like a Dirac Hamiltonian, but in one dimension. So first let me start with the material, and then we can set up the equations. So this material is like a carbon, and like carbon, we know that this is like this sp3 hybridization. We can do it in like 3D as diamond, 2D as graphene, and we can also do the same thing in 1D. And in 1D, the structure is something like this. There is a carbon, 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 something like that. You put these bonds, and it goes on like this, dot, 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 dot. And what this material does is it spontaneously what we call dimerizes. So this bond, like chemists call them like a double bond, like this and like this. And the additional bond is provided by hydrogen, like this. Hydrogen, 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 and so on. But of course, like when I need to choose which one to dimerize, I have two options. This is what I call, let's call this A configuration, A config. But I could also choose like a other bond to dimerize, like this one, and so on. And this is what I will call B configuration. Okay. And these two different minima, what I call like energy minimum configurations, are going to be the key to understand the low energy physics of this material. So typically, this is a gapped material. This is like gapped. It is kind of like a plastic, but a little bit different from this common plastic. This is gapped. What this means is it is insulator. But what we can do is we can dope it, and then we can change it from insulator to conductor. Change to conductor by doping. And here's an interesting and also like a puzzling, maybe in the early days, experiment about this. So this one is, let's say this is doping in arbitrary units. Let's not worry about like details too much. And this one is, let me, with the red, let me write conductivity. And it is something like that. You start doping and it jumps, like initially conductivity is 0 because it's an insulator. And after that, with doping, it goes something like that. Okay. And typically, at least in condensed matter, we are used to like charge conductivity, right? The electrons flow. When electrons flow, we know they also have spin. Spin also flow. And one can also do the experiment to see if there is any spin. And for this, you can do magnetic susceptibility. Let me show it with magnetic susceptibility. And it follows, initially it's like 0, right? It's something like that. Later it jumps like that. But the puzzling thing about this is like you have like a charge degree of freedom, like charge flows, but there is no spin, right? So what we call this, like there are like some charge carriers without spin. Right? These are still electrons. There is no difference. We are still, this material still has like electrons. Some of them are contributing to bonding. Some of them are delocalized. But somehow, in the experiment, you don't see that. Okay, this is one puzzling aspect. And another thing is like sometimes, if you dope it in some region, you can have actually spin degree of freedom. You can have spin without a charge. Not this experiment, but some other experiments which I'm not going to mention, without charge. So what we see is like spin charge separation. So the goal here today is like to formulate a model for this material and at least have like a preliminary understanding of spin charge separation. And this material seems to be like a very good material. For chemists, I think they have different motivations, but for condensed matter physicists, if you want to understand band theory, electron conduction, like insulators and metals, it seems like a very simple yet very rich model. And we are going to try to demonstrate it today, but also later. Okay, this is not today. I will not say nothing about topology today, not today. Maybe when we introduce topology later, it is also interesting topologically. So this will take a little bit while for us to formulate. Okay, so here's the model. The model, a good model, is given by Su-Schrieffer-Heeger. So this Schrieffer is the one who got the Nobel Prize for superconductivity, and I think his son is also a physicist, but I think his son is, if I remember correctly, is like a gravity physicist. He himself is condensed matter, and this is known by SSH for short. And it is like a 1D tight binding model, and it is something like this. Let me draw like a unicell. So there are like two atoms in the unit cell, and like there is like one, let's call this T1 bond, and there's also like T2 bond. Like I will show it with dashed lines, and you can let me repeat. Actually, let me repeat after putting the unit cell. So this is the unit cell, and you can repeat something like that, something like dot dot dot. Let's call this is ETH. I use J, because it's going to mix with complex number J. Unit cell J. This is J minus 1, and this is J plus 1. Now let me use A's for blue atoms and B's for red atoms. And let's also, the bond between A and B in the unit cell is A1. The bond, like the dashed line, is A2. Okay. This is like a non-Bravais lattice, because there are two atoms in the unit cell. Here is the Hamiltonian. Now I think hopefully you'll appreciate this kind of notation, because it's really simple to deal with things like this. And I'll sum over all J. So in the J side, I have like a hopping between like a harmonic oscillator A and harmonic oscillator B. And so this blue can hop to here, or it can hop. Actually, like if you sum over all J, I'll put like hopping from red to blue, and when you sum over all J, you also get this bond. So let me write that. So this is B J dagger A J plus 1, and as before we are going to put Hermitian conjugate. So let me also give some amplitudes for these tunnelings. Typically we have negative, but for this model it doesn't matter. I'll call this one T1 and this one T2. Okay, and what we need to do is like set up the Fourier transforms. A J is going to be defined by this n is number of unit cells, sum over all k, e to the I k, let me call it Rj. So this is the coordinate of this atom, and it is going to be A of k. And now let me also write one for B. So this is Bj is going to be, I'll write it like this because Bj is shifted a little bit. So this is A1, A2. I'm going to write Rj plus A1, and this is going to be Bk. Okay. And I want to look at this term, and Hermitian conjugate will follow automatically. Let's look at this term. And let's take this T1 outside because it's constant. And this one is going to be equal to T1 sum over J sum over K prime K, exactly like what we did last time. And it is going to be e to the minus I K prime Rj plus I K Rj, and let me write this A1 separately, e to the I K A1 and AK dagger BK. And I think I forgot 1 over n's. There's also, let me push this just a little bit. There's 1 over n coming from here, 1 over n squared root coming from here. They add up to 1. Oh, k prime. This one is k prime. Oh, k prime. So this one is k prime, right? Yes, thank you. And so let me try to see. So I think this vector, right? There is 1 over n. There is sum over j, and this is going to be e to the I k minus k prime Rj, and Rj runs over all unit cells. This is going to be delta k prime. And when I see delta function, that's good for us. We write this as k T1 e to the I k A1 AK dagger BK. So that's the first piece. And the second piece is similar, but we have to be careful to get the factors right. So this is T2, and this is hopping from Bj to Aj plus 1. Did I get that right? Yes. And this is T2 1 over n, again sum over j sum over k prime k. So Bj is going to be e to the minus I k prime Rj minus I k prime was it A1? Aj plus 1 is let me write and see, e to the I k, this is Rj plus 1, and this is the first one is now Bk dagger, and the second one is A, so this is prime and this is K. But this Rj plus 1 is Rj plus A1 plus A2, right? They are like 2 unit cells shifted. And the delta function is going to be, and okay, this and this, we are going to combine it to e to the minus I. Actually, let's first get the delta function and then combine. So delta function will be coming from so this, I'm going to take this piece and I'm going to take this piece of exponent, right? And this is going to be delta k prime k.
Do you represent EJ dagger in the same way with you represent with plus A1?
Yes, yes.
But are you representing it with respect to AJ plus 1?
Yes, yes. I think, do you see I have like BJ, I shifted it like this, and here...
Is it going to be minus A1 now, or are we still using with plus A1?
So this is the term,
Yeah.
right? And BJ I just copy from here,
Yeah.
and AJ I just copy from here, but whenever I see J, I put J plus 1. Now I do nothing else. Is that your question? I don't do any tricks. I just substitute.
I wonder if you just represent with respect to A of J or A of J plus 1. If you represent with respect to A J plus 1, you're going to use the minus A1.
But A and B are different objects, right? They have their own Fourier transform. I write it like that. Some people, they say even and odd sides. I get confused when I do it like that, so I prefer to do it. But you do your way. I think if you get the result right, what you say, that's also fine. And so this is going to be sum over all k. Okay, now I can combine these exponents. These exponents are like what? E to the minus I k a1. So I took care of this one. Plus I k a1 plus a2, and this a1 is going to kill this a1. There is only plus e to the I k a2, e to the I k a2. So this one was a1, this one is a2, and this is bk dagger ak. What's that? T2, yes. So here is T2. And we are almost done. Like this H is then sum over all k. So let me write this. T1 e to the I k a1 a k dagger bk plus T2 e to the I k a2 bk dagger AK plus Hermitian conjugate. And this is exactly like graphene, right? There's no difference. In the graphene, we also define some f function, which we are going to do in a little bit. And then the reasonable thing for us to do is like write this in like a matrix form. So this is sum AK dagger BK. So there's like some matrix. So here is AK BK. You can see AK and AK dagger, they don't couple, so the diagonals are nicely 0. And for the off diagonals, I have like here T1 e to the I k a1. So this one is T2. Actually, I am going to write it like conjugate. So here is the Hermitian conjugate of this thing, which is going to be T2 e to the minus I k a2. And if I define f of k exactly as in the graphene case, put this here. So this is f of k, this is f star of k. Let me check if I get it right. T1 e to the I k a1, T2 e to the minus I. It seems like correct.
Where is the B dagger?
So like this one, right? If you multiply, this is, for example, let's do this one. This is f of k, and this is 0, so there will be only, this is bk. And if you multiply this with this one, there will also be ak dagger from here. And from here, it's going to be the complex conjugate of this.
Where is the B dagger in the matrix? First vector has bk dagger as well.
The first vector, oh, this one's yes, thank you, yes. So now and whenever, we have like a matrix like this, we know how to find eigenvalues. Eigenvalue is going to be plus or minus absolute value of f of k. And we can calculate the absolute value with a little bit algebra. Let me just write the result. Right, this has like real and complex parts, and I think I find this to take out one of the a's outside, because when you take the absolute value, total phase doesn't matter. I write it like this: e to the minus I k a2 t1 e to the I k a1 plus a2 plus t2. And now this one is not going to matter because it's overall phase, and the absolute value is going to be t1 cosine. Let me call this a1 plus a2 cosine, maybe cosine a1 plus a2 squared plus, and there is also so this is the real part, and imaginary part is t1 squared sine k a1 plus a2. Did I get that right? Yes. t1 cosine, and this is t2. Right, this is t1. I need the t2 somewhere. Okay, t2 is here. t1 plus t2 cosine squared and t1 sine squared. I think that's correct. There's also sine square, right? And you can open the brackets here and do some algebra to find this is going to be plus or minus t1 squared plus t2 squared plus 2t1 t2 cosine k a1 plus a2, and close like this. Let me show you what this looks like. I'll choose t1 to be 1, and I'm going to define some function, and hopefully you can see it's a little tiny, but it can be seen. This one I defined k, and so this is actually k times a1 plus a2, but let me not write that. So this is t2 is equal to root. When I take t1 is equal to 1, it's going to 1 plus t2 squared, right? Which is ratio plus 2t2 times cosine k. I think that's how I defined here. Yeah, a1 plus a2 is 1 at the moment. And I want to plot this thing, plot k t2, and let me substitute. Okay, so we need to plot this one, and it is minus because there are two eigenvalues, exactly like in the case of graphene. So this one, so this is minus, and here I want to substitute, I don't know, let's start with t1 0.1, and I want to plot this from k minus pi to pi. I took t1 to be 1. If you want, it is here. Let me actually write it and see where it is. It's going to be t1 squared, t2 squared, and it's going to be t1, t2, something like that.
I was asking for the plot. You have chosen t1
t2, right? T1 is, I choose t1 to be 1, t2 to be 0.1. Is that okay? So actually, there'll be too many things. Let me put 1 here. So this is 1. Here, let's plot from minus 2 pi to 2 pi.
And k should be t, I guess.
T?
E of t, t3. First t should be k, I guess.
Oh, yes. Yeah, absolutely. Let me see if that works. Oh, yeah, I think that works.
Does it mean this electron tunnels more to the right and less to the left?
No, we'll come to that. Right now, let's just get the result out.
Okay.
I think the entire second hour we are going to talk about what electron does.
Okay.
But for the moment, let's take one step at a time. And let's put, for example, T1 0. Seems like this is, yeah, okay. Now I can manipulate and show you how it looks like. Manipulate this thing. Now I'm not going to substitute this anymore. So I'm going to erase this piece, put a comma, and let's manipulate T2 from 0 to 2. Okay, so this is the first one. Let me, so this is T2 over T1 is equal to 0, right? And let's take this a little bit. Let's see, this one works 0.5 maybe. And 0.5, you have like this, if you want insulator state with gaps open. But I think the interesting one I already played with yesterday was this one. T2 over T1 is equal to 1. You can say this is gapless, right? So you can see this is flat bands, and I think the last one, let me give you one more spot and I'll explain. So let's cancel that. Let's take, this is 1.5. What do you think will happen if I make this 1.5? Conductor.
So the conductor is
And it's going to be even better conductor?
superconductor?
No, not like not that much. So it happens to go back to that thing. So let's see. So this, okay, let's talk. This one is T2 is equal to 0. This is what we call is extreme dimerization. I can put this side. So this one, if you want, these two sides are coupled. The next one is not coupled. This one is coupled. The next one is not coupled. So if you want electron, if you put in one of them, it just stays, right? It cannot go anywhere. As a result, it has flat band. And if you calculate, for example, the group velocity, del E, del K, like we did last week, this is going to be 0. So this is going to be insulator. Insulator, no matter what the Fermi level is. But typically, Fermi level is where? The Fermi level is right in the middle, right? Because we have like as many electrons as carbon atoms, and at half filling, if you remember what we talked last week, we are going to put Fermi level right in the middle, and if this is the Fermi level, this is an insulator anyways. The second one seems to be, if you want, what we call semi-metal, but we have these like Dirac points. And typically this model and a simple model without any dimerization is indistinguishable. And here we have these Dirac points, and energy is like proportional to some velocity Fermi time. See, there is like a linear velocity here. And because this is just like a jargon, right? When conduction band and valence band just touch at one point, people decide to call this semi-metal, and it is called semi-metal. But it is actually not like anything we had in the solid state. Right? There's like one point, and you have Dirac point, and you have actually some emergent relativistic electron, which is distinct from like usual things we do in like for example Ashcroft memory.
And its
But
conductor is
It will come to that. If it is conductor or not, it is much more complicated. Right now, we just setting up terminology, and I didn't make up the terminology. People call this Dirac point. That's what it is. This is semi-metal. Okay, I'll call it semi-metal then. So this one is back to insulator, and if you see, this is actually like a gapped Dirac, right? Dirac spectrum doesn't have to be gapless. It can also be gapped Dirac points, and we have basically a gap here.
It starts open up from 1, right?
It starts?
It starts opening the band gaps.
Yes, band gaps are open whenever T1 is not equal to T2, right? So gapped when T1 is not equal to T2. You can play with this script in anywhere, and that's going to be the case. Now I want to look at the one limit, and maybe after that I can close this session. So let's consider T1 is equal to T2 and A1 is equal to A2. Then E of K, right? You can easily manipulate the spectrum above to get this one, plus or minus. T1 plus T squared is going to be 2 plus 2 cosine 2 Ka, right? A1 plus A2, there will be 2 AA. And you can take this 2 outside, so this is 1 and 1. So this is cosine square Ka plus sine square Ka. This one is cosine square Ka minus sine square Ka. And this is going to cancel this. At the end, there's like 2 of these, but inside the square root. So this is going to be plus or minus 2. Let me take the absolute value because there's square root cosine Ka, right? We have exactly the cosine band we had, but we take the absolute value and we take plus side and minus side separately. And let's draw this. Oops. So let's draw the cosine band and do what this spectrum tells us. So what the spectrum tells us is like we have these pi over A to minus pi over A. So this is energy. And we have this usual cosine. But when you take the absolute value, right, this piece is going to go up like this. Let me write it with a different color. So when you take the absolute value, you are going to have something like that. And there's also the minus part, and minus part is going to be something like that. Right? Actually, the cosine band we derived in day 1 already has Dirac point, it seems like. And this is the positive, this is negative. And so this is, these colors are dimerized. The black one is undimerized. And what is happening here, to understand, I need to remind you the so-called folding. Let's introduce folding. And this, after that, I'll give you a break. So let me start with usual parabolic band. And the usual parabolic band is something like that, right? You have just free particle, and let's consider, just forget about m's. E of k is equal to k squared, usual parabolic band. And what we do is like we introduce like a periodic potential with A, right? Then that means we need to choose these break points. If you want, this is minus g over 2, so this is g over 2, which is pi over A in our case. And in the like central equation, you just shift these, right? You just shift these because any energy shifted to the right and to the left are going to be the same. and you shift it like this, something like that. And at the end, so this piece, so we are going to open gaps here and here because of the periodic potential, and you are going to have this first band, and you are going to have this second band, and so on. Quadratic band. But we can do the folding for also for cosine band. So let's fold cosine band. So initially we have like this, and like I have something like this, right? And periodicity is initially is A. That means h of A is equal to h of x is equal to h of x plus A for any x. But nobody forces me to choose the unit cell with one atom, right? Even if it is like undimerized, if I feel like, right? If I feel like I can choose the unit cell to be this rather than this, right? Everything works. Like there is no rule in condensed matter books to choose this compared to this one. So when you choose this one, you double the unit cell, and then this means that there will be these Bragg conditions, and you need to shift it like this and like that, right? And if you double the unit cell in real space, what happens to Brillouin zone in the reciprocal space? You halve it, right? If you take the twice, so this is minus pi over A, so this is pi over A. You just halve it in the real space. So this is pi over 2A to pi over 2A. But because of symmetry, which we are going to talk in the second hour, we have these like degenerate points. And the Dirac points emerge automatically from this folding procedure. Okay, so maybe we can take like a 10-minute break. And in the second hour, I'll draw the Dirac equation, and I'll answer your question, what happens to electrons? What is the electronic degree of freedom in this model?